Do. You'll be cutting all of this out, which is awesome.
Hello and welcome to the Hackaday Podcast. I'm Elliot Williams.
And I'm Al Williams.
This is episode 291, Walking in Space, Lead in the Earth, and Atoms under the DIY Microscope. This week, not super much news, so we're going to take a second to plug Supercon. It's coming up in just under a month now, November 1st through 3rd, Pasadena, California. 500 of your closest hacker friends are going to be there. I don't know. We have a lot of people who come every year, and then we have 50-50, I guess. I don't know. I don't actually know the breakdown, but I think a lot of new people and a lot of old people. It's absolutely fantastic to see new faces too. So if you haven't ever been to a Supercon, consider yourself invited. I've invited you.
I think, too, it's fun that a lot of people meet for the first time in person there, but maybe they know each other from the bits and bytes of the online world, so that's always fun.
Oh, God, that's my favorite thing to see when, like, people who've been working with each other for, like, a while even over the internet are, like, all of a sudden face-to-face. It's just so, aw. And when people who should know each other but don't meet in person, it's like that's my absolute favorite. It's like, oh, you're working on this? You're working on this. You should get together and talk.
I'm pretty sure James Newton and I had never actually physically laid eyes on each other until Supercon, and yet we knew each other very well because we were both very involved in the microchip PIC community back when there was a big microchip PIC community among the hobbyists. Well, so have you done your SAO badge for the conference yet?
I maybe. It depends on what you call my SAO badge.
Okay. But do you have something that plugs into the main badge? I know you're a driver behind the main badge, but that's cheating. That doesn't count.
Voya did most of the work on the main badge this year. Last year, I did some of the like design work and the circuit stuff, but this year he's done it all. So on the main badge this year, I took a back seat, but I did make an SAO for the badge.
Oh, cool. I'm holding one of mine in my hands, but I must admit I got lazy, so.
No, you didn't. I saw yours. You way overdid it.
My goal was to do one and actually like do the board on the CNC machine in the shop and hand solder it, and I just said,
oh my God,
I don't have time, and especially to do any number of them. So I just had them made, but they're nice, they're good enough. So you're going to give us a hint about yours, or?
I know we were joking about it, but I still want to just like throw one in the acid and cut it out by hand and make a totally handmade one just for artisanal SAOs. Yeah, no, the gimmick with the badge, and this is maybe a teaser. I hope we get photos this weekend and can write it up next week. But even if we don't, the gimmick with the badge is that it's got a whole bunch of places for SAOs to plug in. And we're giving you some SAOs to stuff in it. And one of them was done by Voya. It's really pretty. One was done by ToddBot. It is cool and interactive. And one was done by me, and it's a blank slate / proto board, basically.
Cool. You've seen mine. I'm no artist by any stretch of the imagination, but yeah.
It does what it needs to.
As you spitefully pointed out, my CPU on my part is probably more powerful than the badge's CPU. So yeah, it's kind of a fail in that respect. It
doubles the amount of CPU power on the badge to have it. But that's awesome. In fact, I think the secret theme about this year's badge, the main obvious theme is the SAOs, but the secret theme is the underlying I2C functionality and having people play around with I2C. And I know you got deep into the weeds on trying to turn your SAO into an I2C device. So not the microcontroller, but the device itself.
Yes, and there will be a post forthcoming in the next probably week.
Like there's so many little widgets you can buy already that speak I2C. And so it's really great to have it in your toolkit, but also it's really neat to play around with making the devices themselves. So imagine you want to, read some analog sensor and then speak back to another microcontroller about it. Writing that device yourself is actually really useful, interesting, and quite empowering. And that's one of the secret educational goals of this year's badge.
Well, that was kind of my goal with mine, was to have something that you didn't have to write any code to use, but if you wanted to write code, it's a peripheral to your code, but it also has a standalone function. So. And I did get there, just to give you a hint, there is a Hackaday I.O. project already for it. And I got a comment on Hackaday I.O. that said, I think it's awesome you wrote a user's manual for it. So, of course, as usual, I've overdone it, right? So,
good for you. Well, it's better than my work, which has no documentation. So
Yeah, I'm a serial documenter, sadly.
you're a good man.
No, I'm forgetful, so in a year I have to be able to read my own documentation or else I'm done. So it's really quite selfish. People think I do it from altruism, but it's actually Alzheimer's. So
That's a secret superpower, though. If it's not a bad motivation to have if it gets the job done.
This is a journey into sound.
What's that sound?
What's that sound?
All right, well, let's head on to What's That Sound? Baffle our listeners out there. This is a Guess the Sound week, so I'm going to play a sound. You in the audience and Al Williams will all get a chance to guess at what it is, and we'll pick among the correct answers next week for a chance to win a Hackaday T-shirt.
I think I'm like 1 for 99 on this, right? I got the Star Trek phaser. I have gotten close a few times, but all right, here we go. Well, I have to say, after the paper tape punch, which you already had, so I know it's not that, because that would have been a pretty good guess for this one, I think. Hang on.
That's right.
It sounds like either a KSR/ASR 28 or 33 teletype, and it's doing the line idle, and then somebody's hitting the key, then a more line idle and another key. That's my guess.
That's a great guess. It is from a totally different corner of technology than that.
Okay.
I'll tell you what it is, but not the audience.
Of course.
It's actually an old
Oh,
kind of 1930s era.
wow.
Well, if you out there know what the sound is, head on over to hackaday.com/podcast. Scroll on down to where it says, What's That Sound? Fill in the form with your handle, your best guess, and your email address. Because if you get it right and then we pick you, I will get in touch with you to get you a Hackaday Podcast T-shirt. All right, well, let's start off the hacks this week with a super deep but surprisingly simple science project. This comes from MechPanda, or at least the video and rebuild is from MechPanda. It's actually a copy of a Dan Berard design from 2015-ish. It is building a 3D printed scanning tunneling microscope. And scanning tunneling microscopes are absolutely insane. They won a team of scientists the Nobel Prize in 1986. You basically take a needle as small as you can make it and you pass it over the surface of a metal, put a little bit of a voltage on it. When it gets just close enough to the metal that the electrons can tunnel through the air in between them in a kind of quantum mechanical sense, the little bit of current goes through. And when it moves a little bit further away from the surface of whatever it is you're probing, less current goes through. The deal is, though, you can pick out individual atoms here. And this 3D printed scanning tunneling microscope was made on a it looks like, he didn't say exactly, but looks like about $100 budget. And he's able to image the individual atoms in a graphite sheet and see that they're hexagonal shaped. And if that doesn't blow your mind, well, your mind is not blown easily. Scanning tunneling microscopes are insane. But like I said, it basically just amounts to making a superfine point, figuring out how much current's going through it, and then moving it, scanning it across the surface. And that is as easy or as hard as it could be. In this video, MechPanda put out a 3D printed scanner body for this. And that's kind of his addition to this project here, is using actually carbon fiber PLA, because it has particularly good thermal stability, to make the body of this thing. What's left is actually a really cheap stepper motor. It's one of those $1 stepper motors, a piezo disc to do the scanning. And this is really cool. This is the old Dan Berard trick, though. And actually, I think was done this way in the original version. To take a piezo disc and just cut it in 4 parts. So, you slice it here, you slice it there, and then you get 4 little piezo discs. You attach wires to those, and then you connect them together. And then by putting voltages on the piezo discs, you can move the scanning point by deflecting each of the 4 quadrants, more or less. The trick is then, writing the code to move them around and getting it exactly as close to the surface as it needs to be to start getting this tunneling current through, but not run the point of your needle into it. Getting a super sharp needle is tricky, but actually you just buy some tungsten wire and you practice snipping it. There's some more sophisticated ways you can actually etch a super, super sharp needle, and I'll throw a Hackaday post to that in the links for you. But you can just do it with clippers and pulling real hard. You might have to try a couple times, but you'll get it eventually. The rest is like, it's a preamp to figure out what the super small current is, the logic to move it around, and that's it. Oh no, there's one more super important detail, and that is the vibration isolation system. Because you're measuring, sub nanometers here, any sort of wiggling or thermal expansion or whatever is disastrous for your scans. And so you need to have it on a really nice isolation platform. This is one of my favorite details here, is that both the Dan Berard implementation, MechPanda's implementation, and the original that won those guys the Nobel Prize uses a platform suspended on springs with an aluminum plate underneath and a bunch of surplus hard drive magnets underneath those. And so it makes, how aluminum conducts, and so if you put it over a magnetic field, it makes the opposing currents in the aluminum and it dampens it out. And this is actually how the folks who did it for the Nobel Prize designed their prototype, with magnets stolen out of old hard drives. So this implementation is both true to the original and dirt cheap and hacky all at the same time.
I've seen these for years, and I'm always wanting to do this, and I haven't done it yet, so maybe this will push me over the edge. I used to have access to scanning electron microscopes, and this isn't the same thing, but it sure is reminiscent of it, and I miss having the ability to go put something in a SEM when I want it. It's interesting that if you read several of these write-ups, the real expense in this is not the components. It's getting something that you can actually measure, like the sheet of graphite, right?
Yeah, right? Yeah.
That turns out to be probably the most expensive thing. I understand, I've seen that before, where you pull on the tungsten wire and cut it and you hope it fractures diagonally. But we used to actually make points for microprobing. I used to go look at microscopes and look at CPUs under them and figure out why they weren't working. But we would take a beaker of sodium hydroxide, which of course is a little bit dangerous, under a vent hood, and we had a isolation transformer. So we had, I don't think you could do this today, OSHA would probably have stopped us, but you'd have a alligator clip, you'd clip the needle holder, and you had that tungsten wire in the needle holder, you held it by the insulated part, and you dipped it in the sodium hydroxide. So you had an electrode in the sodium hydroxide, and the needle was the other one. So of course the tip goes in first, right? And it starts getting eaten away. But as you push in, the tip has been in longer than the part just behind the tip, and that part's been in a little bit longer than the part just behind that part, and it just keeps going like that. So when you reverse your motion, the last part just spent a millisecond, or a thousandth of a millionth of a second in the bath, but the tip was in there for the longest time. So of course it got the most eaten away. And so if you do that, 9 or 10 dunks, you can get these beautiful, beautiful pointy needles, which are extremely fragile, of course, right? Like you said, if you drive it into it, under a microscope, it'll make the nicest little curls. We used to call those genie feet, because, like you see in a cartoon, the genie has the shoes with the toes that roll up, right? So that was a genie. You say, a genie footed, I got to go make another probe, and you'd go in the wet lab to do that. So I really wanted to do this for a while, and I just haven't gotten around to it. And who knows? I don't know if I will this time or not, but it certainly looks easy enough. And then that begs the question of, other than to say how cool, I've imaged atoms, I'm not sure what I want to do with it, right?
That method with the pulling the tungsten out of the sodium hydroxide solution is exactly what this device that I was talking about does. The homebrew probe tip etcher makes amazingly sharp needles by Baird Bankovic. That's the one that I was going to link to. So it's exactly that, only it's got basically a 3D printer extruder head to do the putting it in and pulling it out of the bath. So you get a nice repeatable pull every time, which I think is kind of cute. And second, what do you want to image with these? And that's kind of the trick. It's not often that you need to image things down to the atomic level. Whatever it is needs to be kind of flat, like it can't have too much macro scale variation, and it has to be conductive, because you have to be able to, pull the tunneling electron current through it. So, there are a couple limits to what you can do with this. On the other hand, I think just being able to say, I'm looking at the atoms in a sheet of graphite is so...
There's some value to that.
Crazy awesome. And
Well, and in a real lab, you could always cross-section it and goal code it, right? But, realistically, many of us have a goal target with argon gas to do goal sputtering? So I don't.
Electron microscopy is awesome and significantly more kind of broadly usable, I guess, but also orders of magnitude more expensive to play around with. Whereas this is, you can actually get down pretty deep into most metallic things with very simple setup.
Some beautiful imagery, and assuming you can trust atoms, because as we know, they make up everything, right? So
Boo.
I had to work that one in somewhere. My first hack's from Virtual Protocol, and it's a paper written about creating a video game, sort of a Mario video game, using AI. And I say sort of because AI is kind of a new thing, so they're experimenting with how to represent things. It essentially has done something where you do things like, say, run or jump, literally in text, and it draws a frame from the video game that would show you running or jumping. So not really something you'd probably play. But the trick is they trained it by essentially showing it Super Mario Brothers. And it was just frame by frame along with the data that was input. And they said, well, here's the guy jumping, here's the guy running, here he is getting beamed on the head with a coin or whatever. I don't know. I think the reason I found this interesting, and I was trying to remember if it was Dan Maloney that coined the phrase or somebody around here coined the phrase that AI is the worst summer intern ever. And I'm kind of torn. On the one hand, you can certainly get help from the AI doing programming and especially menial tasks, right? I mean, I can't tell you how many times when I'm working on these badges, I'll say, oh, I need to extract these elements from the list. And I could go look up how to do it or play with it for 2 seconds, but I could also just ask ChatGPT and it'll just tell me, and it's generally right, and I'll know if it's wrong. That's probably an okay use of it. I think when you say, please write me a program that does blank, it's a lot harder. And I think, that's certainly the case here, is to say, write me a video game that looks like this. It did an okay job, but nothing that you could actually play. But, my initial thought on that was, well, that's just a bad idea. But as I thought about it a little more, it really isn't that different from having a summer intern or a junior person. If you hire somebody right out of school, no offense to any of the great schools, but you hire somebody right out of school and say, here's some pictures of a game, go write this, and then come back in 6 months and expect it to look good. Well, you're probably not a very good, steward of engineers, programmers, whatever you want to call that. So as you manage people, you find the same thing, right? You kind of have to say, okay, here's some small thing I want you to do. Wait, you kind of missed the boat. I want to redirect you before you keep going. And so I'm not so sure this is any worse than that, right? Now, the question is that useful? I don't know. I recently gave a talk at a local university about that. And, I think there's a big difference between generative AI, where you say, hey, AI, do this for me, and another thing where you use assistive AI, where you just basically say, I'm doing this, but I would like a little help with the menial tasks, right? It's like asking a spell checker, how do you spell accedence or something? You don't know how to spell it. You get close, you get the right answer. That's a lot different than saying, write my story for me, write this for me, generate this picture. So I don't know. And I knew you would have some interesting input on this, Elliot, so I thought this would be a good one to start off with.
A lot of people misread this in the comments. It's not generating the code to play Mario. It's literally just generating the next video frame.
The frames, yeah.
So it's not actually generating a Mario game. It's just generating a stream of video frames. And so you press jump, and it knows, having seen a million Mario games, that when the guy jumps, this happens and then this happens. But there's no underlying code there. And that's what I find both super creepy about this and super interesting, is that it's not actually generating any code. The entirety of Mario is in this image generation network. So there's no logic there. And in fact, if you look at some of their examples, you can see that there's a bit where he jumps off a ledge and he just totally disappears. And then he comes back after a while, because apparently after a few blank frames, Mario usually reappears in Mario Brothers. What do I know? But sometimes they get confused. They go off on wrong tangents, and it's either really fun or really horrific, depending on the situation and your whole feeling about it. I love the crazy hallucinations and the six fingers and Mario winks out of existence and then pops back up on the other side. I think that stuff is awesome because I'm not expecting it to function right. And I love watching broken machines do their broken machining. And so I think it's really super. But like, I still don't know what this is for.
Yeah, but let me point out something to you. I think you are biased by your expectation of what a human programmer would do. And if you think about it, if you could do this perfectly and say, here's an input and here's what the last frame looked like, here's the next frame, that is code, right? And maybe it's not Python code or C++ code, but it is it's a legitimate way you could write that program that way. We wouldn't do it because we know how to do other things. But if you could say, here's this frame, transform it to this next frame, and you did it correctly, that's all it really takes. I mean, think about like the old games, where it was like a video player, the capacitive discs or whatever, and it would say, do you want to pick up the sword? And you'd press the button and it would go to track 92 instead of track 74, right?
Dragon's Lair was that game.
So this is that, right? And, going back to the junior programmer analogy, I remember in college we used to have to write a little bit of UNIVAC assembly language. That tells you how old I am. And somebody had to they said, write a program to multiply two numbers. And one of the other kids actually wrote, I'm multiplying 2 times 5, so load 2, add 2, add 2, add 2,
Yeah, sure. Why not?
And that's legitimate. I mean, it satisfied the assignment. Nobody who wrote that assignment thought that was the answer because, because you just have this background knowledge that you go, oh yeah, we got to do something that does that. But that's what you asked for. So I don't know that I say this isn't code. I think it's not procedural code in a language we know, right? I think it's transforming an input to an output with input, with other input to color it. And I think that's a program. It's just not the program we expected.
Yeah, but the entire game logic is in these gigabytes of hidden weights in their neural network model that you have no idea what they're doing. Calling that code, where code is a set of instructions that do a thing, is, I think, too far of a stretch. I mean, it's data.
Slippery slope either way.
I know it's a totally slippery slope. It's data, not code.
But think about, when you had the old ROM tables, right? So okay, there you go. A TV typewriter. You take the ASCII code, you put it in the ROM along with the address, and you get the row of dots that come out. Is that code?
Well, maybe that's a better example. Maybe the kid who, given the multiply two 8-bit numbers together, gave you the entire lookup table of all of the products, right? Like that's kind of what the AI model's doing to Mario here. It's just like it's got the big lookup table of all possible next frames and it's just running them.
And I will point out too, there's been a lot of academic work on how to explain what the training is done. Although I haven't read anything yet that I could, maybe I'm just too dumb, but I didn't really understand anything I've read. But the reason I'm interested in it is, think about this. It's one thing to have Mario disappear and show up again. But if you ever think any of this is going in an aircraft, a spacecraft, a nuclear reactor, a medical device, it's not going to be sufficient to go, it learned how to do that. No problem. That's not going to be sufficient, or at least it shouldn't be sufficient.
There's also kind of an Occam's razor thing here. Like the original NES game fits on a 32K cartridge. And this thing is like millions of dollars worth of time training the model. And then probably I exaggerate. It probably didn't cost all that much, but tons and tons and tons of data. Generating the video that Mario would actually put out is like, what? I mean, they're gigabytes and gigabytes, hundreds of gigabytes of parameters here. Like it's so many hundreds of thousands of times bigger than the code that generated it. It's the worst idea ever.
Yeah.
Except that it works without understanding Mario, which I think is kind of fun.
Well, and even what's more attractive to the normal people, not us, of course, but to the normal people, is it was done without having to involve people like us, right? So
yes.
I always said at a previous employer who shall remain nameless, I always said there was infinite amount of monkey money, which was to say, oh, if you give us this much money, we'll be able to train a bunch of monkeys to do all these jobs and you can get rid of these annoying engineers. There was an endless budget for that kind of research. But if you just said, let's hire 2 more engineers, oh no, we can't afford that. But we can sink, 10 times that amount in a research project that will promise to let us fire you all. So, yeah.
I think that's actually an important part of the promise of AI, both to mid-level managers who think they can fire a lot of people and to scientists and researchers, is that it's a general problem-solving tool. Next up, a hack and investigation of the Raspberry Pi Zero's power budget. Pi Zero power optimization leaves no stone unturned is a long piece of work by Manaworm. The project motivating this is called Solar Cam Pi. It's a solar-powered remote camera that boots up, takes a photo, and then goes back to sleep for a while. The problem here is that the Raspberry Pi Zero runs a full-fledged Linux distribution, and it takes a little bit to boot up. And with this kind of strategy, you want that to be as quick as you can and to use as little energy as you can, because the whole thing has to work on a solar panel budget. That's the background for this investigation. There's some really neat tricks here. I've tried to make a few ultra low power devices, and a lot of these tricks here ring true to me. One, though, that's particular to the Raspberry Pi / small Linux computer front is disabling the HDMI saves 10% of the power straight up. And so if you're not going to plug the thing into a monitor, you can just kernel flags and in boot up, turn this off, and boom, 10% off your power budget like that. Other minor tips, there's a whole bunch of power LEDs you can turn off. The other part that I thought was super interesting was that Manaworm looks into turbo mode. And so you can run the processor faster, but for a shorter period of time. It uses more power while running faster. But if it's for a significantly shorter period of time, you can still save on the overall budget versus running it slower for a longer period of time. And here, Manaworm finds out that in this particular case, by profiling the device, it's better to run it in turbo mode and have it go back to sleep as fast as possible. And that's actually consistent with what I've done with microcontrollers too. So maybe it's a general rule? Argue it out in the comments. There's some other things that are specific to Linux single board computers, like the operating systems are basically meant to be plug and play with whatever devices you plug into it. So it does a lot of device probing and asking them, hey, what are you? Hey, what are you? And this takes up a lot of time. If you know ahead of time what devices are going to be attached, you can just compile the right device drivers in, pick them, and skip the whole probing thing. That saves a lot of time during boot up. So at some point in this optimization scheme, the thing that takes the longest time is actually just loading the kernel. And so the question is, how can you get that smaller? The answer is compile it yourself with just what you need in there. Doing that, Manaworm reduces the kernel size down to about a third of what the stock Debian was. And the thing boots up in 3.5 seconds. And then the last trick, and this is also specific to the Raspberry Pi devices, their voltage regulator is not particularly efficient when it's fed with 5 volts. It's better when it's fed with 3.6 volts. And so lowering the input voltage into the Raspberry Pi actually ends up with a 20% energy savings at that point. And so you combine all of these together and it's down to significantly less than half of the original power it used to be requiring to get the job done.
Yeah, I was super amused that just cutting off the HDMI port, which I almost never use on anything like this, was
Right?
that big of a saver. So, and you would kind of have thought maybe it would know there was nothing there and not burn so much power. So it'd be interesting to see why that's the case. I think it is pretty common, though, to see things that you go, you think you're going to run slower, but the break-even point is very bad for that, right? Running faster is almost always better because you can go back to sleep quicker. I wonder, though, in the old days when everything was static, that was the big draw to the 1802, was it was completely static, and you probably had static RAM on it because dynamic RAM was exotic in those days. And so if you were on a satellite or something and you said, I want to go to sleep, you literally just stopped your clock. And then when you started it again, it was right back where, if that clock had been stopped for a week, well, when it started again, you were right back where you were a week ago. I wonder how much of that would be possible here. And I think because of the dynamic RAM, probably not very much, right? There's got to be DRAM that's got to be serviced. But it would be interesting to see if somebody could make, whether it was on, I don't know, FPGA fabric would be too much power consumption just from the get-go, but somehow if you could have something like this that was completely static, I mean, it would not have the gigabytes of memory that you're used to now because every RAM cell is fairly big when you're static. But that would be an interesting case to see something of this sort of power running Linux, but with no dynamic elements and could just be shut down at rest, basically, right? Not sleep necessarily, but just stop the clock, everything goes quiescent, and then it starts up when the clock starts back up. I'm not aware of anything that big that does that today, although maybe somebody else knows something. Maybe they'll tell us in the comments.
Man, that was exactly what I was thinking when I was reading this. Is this whole thing is every time it has to boot up from zero. Why can't, and that costs 3.5 seconds. Why can't you just power down but save the memory in a known state and then, jump back up when that's done? I don't know what the answer is to that, but that's what we do with microcontrollers, right? If you put a microcontroller into deep sleep mode, it spends whatever microamps just to keep the memory powered up and then fires back up in a deterministic state, takes up, program counter moves one further down, and you just keep on trucking. And I was wondering why that can't happen with the Pi Zero. I suspect some of the device driver stuff needs to be initialized into known good states and stuff. I don't know, but it's very interesting. I would love to hear if any of our listeners out there know if it's possible to just suspend one of these Linux single board computers.
I can't tell you, every time I see a post from Ken Sheriff, I feel excited. I mean, I really do. I want to be Ken when I grow up. I used to take apart microprocessors. Ken does all that kind of stuff. The difference is I did it with a lab for a Fortune 100 company, and he does it in his garage, apparently. I admire that. He's not taking apart a chip this time. It's inside the F4 attitude indicator. The attitude indicator, it's the artificial horizon. You see them on the movies all the time. On some planes, they're more or less like a little disc, but this one's the three-dimensional golf ball one, so you can actually see. And if you're not a pilot, these things are insanely valuable because it's not always clear which way up is, which I know sounds really silly, but when you're flying and you don't have any visual reference because you're in a cloud or it's at night, then add to that, you're in an F4 going at really fast speeds. It's really important to have this working. I gotta tell you, anytime, you've heard me say this before, like teletypes, I think somebody was walking down the street in Skokie, Illinois, a teletype fell out of the sky and they went, oh, that's interesting, we should make more of those, because there's no way you would say, here's a problem, oh, we could solve it with all this mechanics, right? I'm thinking about the early teletypes. This is like that because there's all these little mechanical contrivances to get this ball to move in 3 dimensions and track all the motion of the airplane and everything, but then add to it that it's in something that looks like it's a little bigger than my fist, right?
Yeah.
And it will take a couple of G's worth of shock because it's in a jet fighter, right? So there's just nothing about this that you can just say, oh, well, that's stupid. Everything's built maximally, and the slip rings and it's just a beautiful piece of design, both electrically and mechanically. One of the things you always see in these, and it's something I don't know why we quit seeing them, other than I guess it's easier to do it now, but there's synchros in this, or sometimes you hear those called Celsons, although Celson's actually a trade name, I think. I think that was Sperry's trade name for it, where you have, a shaft, and you move it, and it moves the shaft over a mile away or whatever that's connected to wires. It moves it the same amount. And so a lot of things back from this era, that's how they did things like that. Oh, I want to turn the antenna to the north, so I move the pointer to N, and then mysteriously the antenna moves to the north, right? Those were synchros, and if you look those up, they're really pretty interesting. Now, you would just say, oh, I have a stepper motor, and I go, oh, command the stepper motor to go to this position, and it's not this direct linkage between shafts. But if you look at any of these airplane systems, Navy systems, not just the war Navy, but, even on a commercial ship or anything, in this time period, those things were everywhere. And, we've done things like on the Norden bomb site. I'm sure there were a bunch of those in there. And it's just a different kind of design. It'd be really interesting, and I'm sure they wouldn't let you do it, but it'd be interesting to tear apart a modern indicator from like one of these super modern jet fighters and see what was in it compared to this. I'm guessing it's a lot less impressive, but a lot more technically sophisticated. But to be able to do all this with just a handful of electrical parts and a lot of mechanical parts and gears and gimbals and all this is pretty impressive. And of course, nobody takes things apart like Ken does. So it's a great The video, I was going to say a great watch, but if you look, the video is like a 20-second video of it actually working and no explanation or anything. So really, you got to read the article. Don't just watch the video, but it's well worth the read.
I was looking at it, I'm like, there must be something we can learn from this, like that'll be useful for mechatronics or something. Like imagine this was an eyeball for like a Halloween prop or something. This could be really useful. No, it is too damn complicated. This is not the way you want to do it. This thing has like what, 20 slip rings in it, and
Slip
a
rings
motor,
inside slip rings
a
too. That's what I
motor
thought
for
was.
each axis. It's an incredible device. Anyway, you go read it just for the enjoyment, but I don't think you're going to build anything like this at all these days.
Well, I am surprised we don't see synchros more because they're stupid simple and they've got to be dirt cheap on the surplus market if you can even find them anymore. But they do have their uses, and I don't know, maybe they are used somewhere, but I haven't seen one in a couple of decades.
Well, last up from me, Will Wong's project, easily build this IMU array sandbox. So you know how they've got all these little MEMS IMUs? It incorporates a gyro and an accelerometer together. Those are awesome, and they're very cheap these days. And so what's better than one IMU? Will's answer is 32 IMUs on the same board. And this is going back to some recent work by Japanese researchers that's actually manifested itself in a Sony project called SPRE Sense, where they take 16 IMUs, put them all together, and then use them to kind of average out the noise coming from each one of them to get a more precise reading. And so Will is taking this up one step further. He's got 32 of them on the board with an FPGA in the middle, that pulls them all for information and combines it together. He hasn't gotten too deep yet into the signal processing here. I think there are a lot of super smart things going on in some of the more professional implementations of this. And so far, Will's just kind of averaging the 32 values together. But he's designed his board so that the IMUs are around the edges, so they're all kind of in a square. They're all 90 degrees to each other. And this has tremendous advantages because if you have something external that causes noise in one, or if the parts are all manufactured so that they have a bias one direction or the other, you've got some on one side and some on the other, and so they can kind of cancel each other out when you do the averaging. I think it's a really, really cool project, and these kind of ultra sensitive IMUs are useful for doing like dead reckoning. So if you want to know where your robot is by where it's gone, if you use a regular IMU, there's inaccuracies in there and they'll drift over time and stuff. The super interesting combined algorithms actually do things like when they get a really large or really small value, they'll throw it away and assume that it's just a noisy response. It's some disturbance in the IMU and not actual data. And so there's a lot of things you can do with that to make the IMUs not drift over time, which is what they do and what makes dead reckoning a hard problem. These things cost like $1 each. The board is pretty fancy. He's got a 6-layer board, and that's to keep the size down. The thing is, I think, kind of 1.5 inches, 2 inches by 2 inches, so it's not super large. Basically, it's take a whole bunch of commodity IMUs, read them together, average them out, and you end up with something that is unspeakably accurate. So accurate that it falls under ITAR export restrictions, and you probably couldn't send it abroad for fear that someone would make a missile out of it.
Yeah, I would think you might not want to make the board bigger because the bigger you are, the more spread there is across the sensors, right? So I think there's some advantage to having them tightly clustered. And I would think you'd make that board a little thicker than normal if you wanted the best result, right? You want as little flex on the board as possible as you accelerate different ways, especially if you were doing something high. Yeah, you're right. If you're on your bicycle, it probably doesn't matter, right?
Yeah, right.
If you're on a hypersonic missile, might matter, So I guess that depends on your use case. I was a little surprised, although as I got to thinking about it, I realized it was a hard problem. It's great that he does have the common mode rejection, so you've got in the X and Y direction, anything that's an external problem should subtract out. but there's nothing on the z-axis, right? But to do that, you'd have to almost make a little board that went vertically, and then the attachment of that board becomes a problem because it's got to be attached in some way that it's not going to flex relative to the rest of it, right? So I don't know. I was trying to think about that. Like, should this have been the IMU cube instead of a flat? If you really want to get into doing the fancy stuff you were mentioning, the Google phrase for that would be sensor fusion, right? Fusion being the word for taking all this data and doing it. I honestly was blown away. I mean, actually, I'm always blown away with these little IMUs, given that the first IMU I ever saw was the size of like a 9-year-old boy, you know?
Right.
And it probably cost the government $28 million or some ridiculous, improbable number like that. So the fact that you can, for $1, get a little chip that, you know, you could smash with a hammer probably and not have a problem is just shocking. So, yeah, I was trying to think of something interesting to do with this, and I haven't quite come up with it, but it looked like a great thing in a small package. All it lacks, I think, is an SAO connector. And my last hack for the week, Treble had a ThinkPad 13. The ThinkPad 13 had an M2 slot in it, but it was keyed to where it would only take a SATA SSD. Well, I say it was keyed. It wasn't keyed. It just would only take a SATA drive in it. And Treble wanted to put an NVMe drive in it. I guess they're cheaper. I think they perform better too, but reading the post, maybe they're also cheaper. I don't know. So there was a time when if you said, well, I have a laptop and I don't like it, I want to change something in it, it was like, well, tough, right? You know, you could probably hardly get into it. And when you got into it, everything was unworkable and you didn't have the tools. But now, of course, we all have microscopes and hot air soldering irons and little tiny tweezers and all this good stuff. And so she was able to open it up, figured out that the SATA drive support was there, but also the NVMe support was there. It just wasn't populated. So handily, there were little spots on the board with little silkscreen brackets on it and 3 0-ohm resistors, you know, basically pieces of wire soldered across 3 pads. And there you go. And then there was also some capacitors they had left off, I guess, because they didn't need them for just the SATA, and that made it a little faster. So, you know, more soldering, no big deal. In of itself, I mean, it's an impressive hack that you were able to just go figure that out, because if you've taken a laptop apart lately, you know, it's pretty daunting. Even for me, I look at it and go, oh, no. I just actually had my wife's open this week, changing out the hard drive in it. And it's like, man, they just packed that stuff in there. And yet we've got things like the M2 sockets where, you know, you can in fact replace the Wi-Fi and you can in fact replace the hard drive. And I think that's great. I wish there was more of that. But you know, on the other hand, I didn't yank the CPU out and figure out where to solder wires to get it to change its functions. So I don't know that this is all this generally applicable, but I just thought it was impressive, and it shows how far we've come in that while this is very impressive, it's not unbelievable, right? If somebody had done this, you know, 20 years ago, you would have just said, that's amazing. How could they have possibly done that? And now you're like, you know, yeah, it's impressive. It's great, but, you know, it's not something you couldn't imagine that you might have done. You've got the equipment that you probably should be able to do it. Whether you would do it or not is another question.
I wanted to start off with the Microphone open source simple smartphone project. This is fantastic. It's an entirely from the ground up feature phone design that you could make yourself. I think it's lovely that you can do this. It uses a cellular modem with not an open firmware, but at least a hands-off firmware. So the cell modem isn't so tightly coupled into the rest of the project that you can use whatever processor you want and whatever you want for the display. It's really, really cool. And I just love the idea that we're at the point where we could make our own smartphones. An entry in the SAO contest, we've got SAOs for your SAOs. It talks about one done by Dave Darko. Simple add-ons are just kind of plugins for your badge. Here he's got one that has a bunch of plugins for yet smaller plugins. So the SAOAO, the simple add-on, absolutely hilarious. So we heard you like SAOs. How about some SAOs for your SAO? And last up, J Summit. Man in the Middle PCB unlocks HP ink cartridges. This is a cool teardown of some refurbished Chinese HP compatible ink cartridges. And what he finds, in addition to, of course, refilling the thing with ink, that what they did is to fool the proprietary chip that says this cartridge has printed so many things by inserting a flat flex PCB with a little microcontroller on it in between the contacts on the printer cartridge. I think this looks like a one-off hacker project, but the fact that this is done on a large commercial ink cartridge refilling scale is really, really neat to see.
Okay, my quick hacks this week. Mustafa has a interesting, I think you could win a bar bet with this. How do you blink an LED without any active components? And the answer is a little bit of a cheat. Maybe it's a hack. I'll let you look at the article to see, but I will say one of the components is a light-sensitive resistor. My next hack up, printed jellyfish lights up from Ben. This is a beautiful jellyfish sculpture, and I did a little research. I guess there is a famous jellyfish kinetic sculpture that looks like this somewhat, but the tentacles move and there's all this fancy LED lighting. And what I thought was very interesting was Ben is 15 years old. So not only is the sculpture really good for anybody, but the write-up was awesome. So, we were talking earlier about documenting stuff. Ben certainly has the gift of documentation, and we're anxious to see what he does over the next 15 years. And last but not least, in the more unthinkable upgrades department, Ken Pillinell adds USB-C to Apple AirPods. Supposedly the easy way, although I'm not sure if there is an easy way, but again, one of those upgrades that you think, man, that should be near impossible, and here somebody does it.
Well, that brings us to our Can't Miss articles. These are long-form pieces written by our fantastic Hackaday writing staff. This week I picked Tom Nardi's Polaris Dawn and the Prudence of a Short Spacewalk. Week or two ago, Polaris Dawn was a private SpaceX mission that had the first private spacewalk it was billed as. And if you look at the promotional material, they've got, a dangling spacesuit out the front of a capsule. The reality of it was that they opened the capsule and, climbed a little bit of a ladder, peeked a head out into space, but, no waste went into space on this one. Certainly no feet. Calling it a spacewalk would be insane. Calling it an extravehicular activity is a half-truth. I mean, they were only half out of the vehicle. And Tom's point of this whole article is that's really great, because this problem is harder than you think. And there have been a lot of EVAs that have gone wrong. And if you're going to start doing this, especially testing out a new pressure suit, especially doing the first time you vent the entire capsule to the vacuum of space and then have to close the hatch again and repressurize everything again, there's all sorts of reasons you would want to take baby steps here, and he goes through them through historical examples in this article. And I think that was the part that was neat for me, because I didn't know about the history of EVA's, extravehicular activities. The first ever EVA was in 1965, done by Alexei Leonov, at the time the USSR. And he gets entirely out of the capsule, but they underestimated the pressure on the suit, and he finds his suit ballooning up so that he can barely get back in. The climate control also didn't work on his suit, and so he's stuck outside with an inflated balloon around him, sweating out of control, can't see anything because his thing's fogging up, and then he has to manually deflate the suit way below the safe quarter atmosphere to get it to shrink down enough and so that he could move in the thing enough to get back inside the airlock. And of course, because this was Cold War times, the USSR doesn't say anything about the troubles they had here. It's like glorious victory, first spacewalk. And so we didn't know anything about it. And then NASA does their first EVA shortly thereafter, actually, 3 months later. And this one was really cool because it had that, I don't know if you've seen the little handheld maneuvering unit that sends out puffs of gas to have, in this case, Ed White, the first American EVA spacewalker, maneuvering in space on the end of his tether. Really, really cool looking, very 60s spacey. And he had troubles too. With his, there were, again, two issues. The latching mechanism that opened and closed the latch was known to be troublesome, and they almost thought about aborting it, but this was the 1960s cowboy astronaut mentality. they didn't tell ground control that they were having trouble with the hatch. The other astronaut in the Gemini capsule, James McDivitt, actually knew how the latch mechanism functioned and guessed that he could make it work. And so they managed to get the thing open without telling ground control. Ed White went out for, this fantastic EVA, comes back in, and they can't get the thing closed again, right? And during this time, they'd gone around the backside of the Earth, and it's dark. And so they're fuddling, trying to close the hatch so that they can repressurize the capsule because, well, I mean, first there's the pressure, but second if you can't manage to get the hatch closed, you're going to have a bad time returning to Earth. Long story short, they fixed it, but never told NASA about it. Which brings us a few years later to Gemini 9, where they had other problems with the suit. I guess the suit here had trouble with temperature control, and like with Leonov's, there was no way to deal with it because this was an air-based, like air conditioner in the suit, and was just not up to the task. Gene Cernan nearly died, had not enough energy to get back in, had to rest for a bit. I mean, it was almost a space disaster. When he got back to Earth, Tom says he lost 13 pounds during his spacewalk, which is absolutely terrifying. Because the Russians didn't admit to their problems with the cooling, and because the previous Americans kind of covered some of their problems under the rug, I think there were all of these failure points that could have bitten people along the way that probably should have been more openly talked about, discussed, and engineered around. Me armchair quarterbacking the space race. So take that for what it is. But in that context, then, Tom finishes up by going back to Polaris Dawn, and he's like, yeah, so, all they did, in big air quotes, was open the hatch and peek out. But opening and closing the hatch is a super critical part of this mission. Whether the suits hold pressure and whether people are able to move around in them, whether they balloon up so that the people can't move, whether they can't keep people cold, whether there's, perspiration built up on the inside of the helmet. Like, there are all of these near emergency points, and it makes sense to take a small conservative first step like this. And actually, in that light, I think I'm going to put less ridicule on the first Polaris Dawn spacewalk ever.
Yeah, we're spoiled because the movies and TV make it look like all this is just super simple, right? You jump on a rocket, you go to the moon, you put on your spacesuit, you open the door, you jump out, you plant the flag, it's nowhere near that simple. Spacesuits are terrible, and the reason spacesuits are terrible is because the environment is terrible. So what you really want is you want something that will protect you against anything, but then now you're walking around in an armored tank, right? And you can't do that. So now you've got to have something that flexes. The problem is you don't have constant volume joints. We don't know how to make that yet. So think about this. If you take a balloon and you've got it pretty full of air and you try to tie a balloon animal in it, what happens? You can't, right? At some point, the balloon's so full of air, you can't bend it any more than a certain amount. Well, you're inside a balloon. So the answer is, don't put so much air in it. Well, great, except you also need air. So if you ever hear, like I watched 2001 A Space Odyssey the other night, first time I've seen that in years. And, there's all those great scenes where he's in the spacesuit and is, that's not because they're exhausted. It's because they don't have any air in there. And that's why they train them up in the high mountains and stuff, is they're very low volume of air in those suits, because otherwise you would hardly be able to move. And if you did move, you'd be exhausted because you're basically bending these giant balloons. You mentioned the condensation problem. There's been some famous cases recently where suits started filling up with water. I imagine that's a pretty good nightmare, right? The water's up to my waist now. I'm sure that's going to be fine. And of course those were problems, right? I'm not saying they do that normally, but it has happened. At one point too, because you've got the low pressure, you're subject to getting the bends, which is when you have nitrogen bubbles dissolve out of your bloodstream. So on those early flights with Lieutenant Colonel White and that bunch, I don't know what the Russians were doing, but they had all oxygen. And so you were breathing pure oxygen anyway, so there was no nitrogen in your blood, and that wasn't as big a problem. But, on the shuttle where they didn't do that, because you realize Apollo 1, that was one of the causes of the fire was the pure oxygen. And of course, Colonel White lost his life in that fire. But, they would have them sit and breathe through a little breather mask for, I don't remember how many hours, but it wasn't, it's not like you could say, oh, quick, get your spacesuit on. No, it's here, quick, breathe into this mask for 12 hours and then put your spacesuit on. So there's a lot of little gotchas to this that you just don't think about. The condensation is amazing. If you ever watch any of the video, like the space shuttle docking with the station, what you don't realize, unless you were paying very close attention, is they don't dock, throw open the airlock, and walk through, right? Because the problem is you've got relatively warm air full of moisture hitting this ice-cold metal that's been out in space 10 seconds ago. So essentially it rains inside that tunnel. And even after they wait for it to kind of stabilize, if you notice the astronauts go through there, they're wiping all the equipment down as they go because it's all just super wet from the condensation from the atmosphere that they're pumping into it. So, I mean, again, all those things, when you know about them, you go, oh, yeah, that makes sense. But, you didn't think about that. And the expanding spacesuits, even the little AMU, that was good, but it really took Bruce McCandless, and when was that, the 90s, and the MMU to really give them true mobility. That's the thing that kind of looks like a chair they're sitting in, and it's almost a little spaceship. Very cool stuff. So, this is one of those things where if you watch the movies, you think, oh, sure, me and my hackerspace, we could do that, no problem. And it turns out it's all these very difficult things that have to be solved to do that. So good job to SpaceX. I mean, yeah, I granted they didn't get out and tap dance on the surface. I understand that they didn't have micrometeorite shielding, so they had to make sure they were behind the nose cone and all. There were a lot of concessions to make sure that they were not putting that astronaut in danger. But good for them, right? They shouldn't put the astronaut in danger, and you got to take the baby steps. It's not a Bruce Willis movie, so good for them.
Yeah, I think Tom summarizes that nicely at the end, where he's like, they did it all on live TV, so there weren't any cover-ups, but you also know there weren't any unnecessary risks taken, and none of this like 1960s cowboy bravado.
Now they're probably flying with the representative for the insurance company in the next seat, right? Well, my pick this week might not be technically a hack, but I really enjoyed it. It was Dan Maloney's Mining and Refining Lead, Silver, and Zinc. Dan's one of those guys, right? I mean, as am I, where he just seems to like to know where things come from. So I don't know that Dan's ever going to go out and mine galena ore and refine lead from it, but I can tell he likes that he knows how to do it. And I'm like that too. I'd heard a lot when all the anti-lead legislation came down in the EU, and I'd heard people say, and I can't verify this, that the electronics industry contributes a minute amount of lead into the environment compared to balance weights for car wheels. And I would imagine that's true, right? There's just a bazillion cars that are scrapped every day. But of course, nobody's got the stomach to say you can't use lead weights in the car wheels. So I was amused that I guess Dan's grandfather used to collect those, melt out the steel parts with a propane torch while Dan watches. Another OSHA case that would be today, and use that to make lead to go sell for scrap metal. So I thought that was an interesting story. I think the larger thing to this, I mean, definitely go read the article. There's all sorts of interesting things about where all this metal comes from and what it looks like in its ore form, and that there's actually a small amount of silver in your wheel weights, and if you're desperate enough for making silver, there's a way to recover it. Different things like that. But I think what the larger thing I wanted to kind of think about today is when you think about it, we use so much different things that there's got to be these giant infrastructures in place, and most people have no idea, including me. I mean, I think we all know our little infrastructures, right? So probably most of the people listening to us could sketch out a pretty good picture of how our voices are getting from our server to their headphones, right? I mean, we kind of all know how the internet works and all that, but I think normal people don't, right? It's just mysterious things come on my computer for somehow I don't know. Certainly when you talk cell phones, people don't know how cell phones work. And I think it's very interesting to look into these things that we just take for granted. Where do they come from and how is that all done? And I think Dan's Mining and Refining in general has done a really good job from the metal standpoint of where does all this stuff come from? How does it come out of the ground? what happens to it. And I don't think he talks much about how it gets into our hands, but I think that's very interesting that all this goes on. And I don't know why. I can't figure out why this interests me, but it does.
The whole how we get metal out of the earth thing is really wild. And, lead is actually one of the particularly earliest metals that people ever got out because it melts at such a low temperature, right? It's easier to separate the lead from the rest of the stuff. Smelting, maybe what I'm looking for. He says, looking through Dan's, please, Dan, save me. Yeah, smelting.
So this is another thing, though, right? I mean, I don't necessarily see trucks full of lead driving all over the place, but there must be. And certainly where I live, you see train cars full of plastic all the time. But now I think most people probably don't know that's what's in it, right? So there's a train car. What's in it? I don't know. Well, it turns out it's plastic pellets because they make them here, right? Yeah, it goes back to the same thing. I think most people are completely oblivious to all this stuff that goes into supporting our modern life. And, if you ever want a real shocker, just ask a normal person how their cell phone works, and it's pretty amusing. If you're lucky, they'll just go, I have no idea. But if they try to make something up, it's usually pretty funny.
I think I was in grad school and I watched this documentary about the crop circles. The original crop circles were made by a couple drunk British hooligans with a stake, a piece of string, and a board that they used to flatten things. But then all the people who thought they were aliens are all like, they're so perfectly round. There's no way a person could make something so round. And, I'm like, like, A, that's easy. But B, it must be alien technology because it's so whatever. You then make a call to someone with a cell phone after that. And that's freaking alien technology. Like, making circles in somebody's wheat field is not alien technology, but a cell phone is certainly alien technology. And I do agree that I think nobody fully understands a cell phone. You dig deep enough into any one corner of a cell phone and nobody understands it. Yeah, it's alien technology.
There's just too much to know, right? So, and I always say that we all build on abstractions, right? Yeah, sure, I can design a CPU, but I'm not cutting quartz silicon to, crystals to make ICs or drawing my own copper wire. I mean, there's always an abstraction. There's almost nothing you could actually do from first principles of any significance, right? So.
Yeah, absolutely not. And a cell phone isn't made by one person. It's made by, many people and a history of, many people. All of these things evolved from somewhere and, no one person could invent it for sure, but they did nonetheless get invented and came from somewhere. That wraps it up for this week's Hackaday podcast. Thanks very much for listening. If you want to follow the links, head on over to hackaday.com/podcast. And if you see anything cool or do anything cool, write us at tips@hackaday.com. And until next week,
keep those hacks coming.
I got a burp, so hold on a sec.
There's your outtake, though.
Well, that brings us to quick hacks. These are, no, I don't even talk about what these are. It's not what I do. Who was his name again?
Yeah, it's Leonov. Alexei Leonov.
I'm having trouble hearing. Can you say that again?
You triggered my Alexa.
Alexei.
Sorry.
Sorry, something went wrong.
Alexei Leonov.
And I can find my stop button today.
Let's do it. That's a wrap.
All right. Let's counter rotate keys.